world of digital musical instruments opens up a universe of exciting possibilities for performers, songwriters, and amateur musicians, as well as for folks who want to add music to a computer-based presentation or word processing document. This tape will show you how these new instruments are different from traditional acoustic instruments. You'll see some of the amazing things you can do. Perhaps most important, you'll learn what you need to know to buy and use digital musical instruments effectively. We'll examine some of the most useful categories of digital musical instruments: keyboards, tone modules, wind controllers, drum machines, drum controllers, and sequencers. We'll introduce you to general MIDI and standard MIDI files, and you'll see how they link digital musical instruments to the world of multimedia. And finally, you'll learn to set up and troubleshoot an entire system of digital musical instruments. The tape is divided into sections, like chapters in a book. Each section covers one type of equipment or one important idea, so that you can find the sections you want to review. There's a graphic identifier or icon for each section. You'll find the icons on the box that holds this tape. An icon will appear on the screen as each section begins, and it will remain there when you use your VCR to do forward or reverse searches. The most important difference between traditional acoustic instruments and digital musical instruments is that digital musical instruments work not just with sounds, but also with data. It's like the difference between a tape recording of a song I played on the piano and the sheet music for that same song. The recording captures the actual sounds that come from the piano. The sheet music uses data, symbols that tell me what to play. When I see this music notation, I know I should play this note loud and hold it for about that long. The data system used by almost all digital musical instruments is called Midi, the Musical Instrument Digital Interface. It is not a musical language. Instead, Midi is used to control digital musical instruments. Synthesizers are the digital musical instruments that produce sounds. They can be built into keyboards or in separate boxes, like this tone module. One of the things Midi lets you do is connect together two or more instruments so that playing one produces the same notes on both. That way you can produce richly layered, complex sounds, not just the sound of a single instrument. There are two parts to the hardware of Midi. One is the Midi interface that's built into every digital musical instrument. The other is a Midi cable that carries messages from one Midi interface to the next. It's easy to tell if a device has a Midi interface. Just look for Midi jacks. If the jacks are present, so is the interface. The Midi specification includes three types of interfaces: Midi in, Midi out, and Midi through. Each has a female jack designed to receive the 5-pin Midi cable connector. Midi cables carry messages from the Midi out jack of the device that sends the messages to the Midi in jack of the device that receives the messages. When you use the keys, wheels, or buttons on a digital musical instrument, you generate Midi messages that describe exactly what you're doing. Let me show you how I connected this master keyboard synthesizer to control this slave keyboard synthesizer so that we heard both when I played the master keyboard. I plugged the Midi cable into the master's Midi out jack and the slave's Midi in, so that the messages I created on the master flowed to the slave. It's the key to connecting Midi cables properly. The sender's Midi out to the receiver's Midi in. And remember, MIDI messages contain no audio signals. You won't hear anything until you connect cables from your synthesizer's audio out jacks to the audio inputs of your mixer, amplifier, or stereo system. In addition to MIDI in and MIDI out jacks, most digital musical instruments have a third jack called MIDI through. It copies signals a device receives at its MIDI in jack and immediately sends the copies, unchanged, out the MIDI through jack. Later on, you'll see how to use MIDI through to set up a system. A program change message selects a single instrumental sound or sound effect of the many a synthesizer might be able to make. MIDI does not specify the exact nature of the sound that is associated with any particular program change message number. The same program change that selects a brass sound on this synthesizer selects an electric bass sound on this synthesizer. As you'll see later on, General MIDI was designed to address this problem. MIDI controllers make no sounds themselves. Instead, they generate messages that tell synthesizers what sounds to make. MIDI controllers that look like guitars, saxophones, and trumpets are becoming commonplace, but keyboards were the first MIDI controllers, and they are by far the most prevalent. If a keyboard will be your primary MIDI instrument, the choice of which keyboard may be your most important hardware decision. Few MIDI keyboard controllers feature a full 88-key piano-style keyboard. Those that do are generally the most feature-rich and expensive. Other common keyboard sizes include 76 keys, 61 keys, and 49 keys, though some manufacturers make even smaller keyboards. For songwriting, a smaller keyboard may be enough to get the job done, because most synthesizers can transpose in real time as you play. Transposing a note changes its pitch to a higher or lower one than would normally sound when you press a particular key. And MIDI sequencers let you transpose music after you record it. But for live performance, when you want to use the full range of notes, more keys are probably better. Regardless of the number of keys, every MIDI keyboard sends two types of information: keys pressed and keys released, MIDI's note on and note off messages. Although every MIDI keyboard can generate these messages, some can do much more. This MIDI keyboard can detect how fast I've pressed each key, just as a piano does. A velocity component is part of each MIDI note on and note off message, and most synthesizers sound louder with higher velocity. Keyboards without velocity sensing send all note on and note off messages at the same velocity. Some full-featured keyboards send messages that indicate how hard you press a key as you hold it down, called aftertouch. For example, if a keyboard controller can send aftertouch messages and a synthesizer can react to them, aftertouch pressure can cause the sound of a trumpet to waver in pitch as it sustains a note. Many MIDI messages include a channel number used to route the message to a particular device. Channels do not designate data storage areas, but data communication paths. A single MIDI cable can carry messages for 16 different channels at once, just as a single telephone cable can route each of many calls to its particular destination at once. Keyboard splits let you assign one MIDI channel number to the notes below a particular split point and a different MIDI channel to the notes above the split point. Then you can connect two different synthesizers to your keyboard controller and assign each synthesizer a channel number that matches one section of the keyboard. As you play, each synthesizer responds only to messages tagged with its own channel, ignoring messages tagged with other channel numbers. For example, I can play acoustic bass sounds on this synthesizer with my left hand, and pipe organ sounds on this synthesizer with my right. Some keyboards let me assign a single split point. Others allow multiple splits with a different MIDI channel assigned to each group of keys. We use the term controller both to indicate a digital musical instrument like a keyboard controller and for a performance control within that device. MIDI recognizes three types of performance controllers: continuous controllers, bidirectional continuous controllers, and switches. Continuous controllers are usually sliders or wheels that can stop at any position. They control aspects of the sound called parameters that may be set anywhere within a range of values. I often use a modulation wheel to set vibrato depth. The farther I turn the wheel, the more vibrato I add to the sound. Bidirectional controllers usually take the form of a wheel that returns to a center position when you let go. I use one to control pitch bend. The farther I move the wheel from its center position, the more you'll hear the pitch change. When I release the wheel, it returns to the center, and the pitch returns to its original setting. Switches usually appear as buttons or foot pedals that are either on or off. This pedal controls sustain. Pressing turns it on, and releasing turns it off. Performance controllers help you add expressiveness to your sounds and improve the quality of the sounds. I like keyboards that have lots of them. Today, most keyboard controllers also have a synthesizer built in. Strictly speaking, we should call them keyboard synthesizers, but we usually just say synthesizers, MIDI keyboards, or synths. A keyboard synthesizer may be all some people need. They come in a range of sizes and prices. Some are even small enough to fit in the palm of your hand and battery-powered so you can take them anywhere. Some keyboard synthesizers even have a small amplifier and speakers, and most have a headphone outlet built in. Power up one of those, and you are ready to start making music. Although keyboard synthesizers can be as easy to set up and use as a boombox, they are not as flexible or expandable as a component system. Still, a keyboard synthesizer is often a good first choice, even if you're not a keyboard player, because that first keyboard can also serve as the controller for your whole MIDI system. In my MIDI system, I use a keyboard controller and tone module. A tone module is a synthesizer in its own small box, or a sound card that plugs into a personal computer. Tone modules are usually less expensive than keyboard versions of the same synthesizers, so you don't have to pay for synthesizers with keyboards that you wouldn't use. You may hear salespeople talk about direct synthesis, frequency modulation, subtractive synthesis, phase distortion, and the like. but the names really don't matter. Your ears can judge a synthesizer's sound. Use your ears and trust them. If you're looking for the most authentic reproductions of acoustic and electric instruments, you should consider a sample playback synthesizer. They're a special category of synthesizers that play back the digitally recorded sounds of actual instruments. Some sample playback synthesizers let you save samples from the synthesizer's memory to a storage device like a cartridge or diskette. You can share sample diskettes with the folks in your band and build up a library of sample data diskettes. That's something you can't do with other kinds of synthesizers unless each of you uses the same model. To make it easy to exchange samples among different brands of sample players, the Midi specification includes a special group of messages known as the Sample Dump Standard, or SDS. Any sample player that implements the Sample Dump Standard can receive samples stored in SDS format or transmit samples in SDS format for playback on another unit. While we're on the subject of transferring data from one device to another, let me mention another form of data transfer: backup. There is really only one rule governing backups: do it. When power outages and other problems have erased all the data from my system, I've been awfully thankful that I made backups. By loading the data from my backups into my equipment, I can get right back to work without having to recreate all the data from scratch. So save your data whenever you make a change to your system. Remember to do it, and do it often. Midi involves lots of data, and since computers manage data, they can help manage Midi data as well as any other kind. So sooner or later, you're probably going to want to hook your Midi setup to a computer. But that's a subject that deserves its own videotape. Most synthesizers can play polyphonically, that is, many notes at once. Each synthesizer has a fixed maximum polyphony, but the maximum varies from one synthesizer to another. 8 or 12 notes at a time is common on low-cost synthesizers, while more expensive models may have 24-note polyphony or more. A multi-timbral synthesizer acts like several tone modules in a single box, able to play different instrumental sounds, often called voices, at the same time. Each voice is assigned its own Midi channel. Remember keyboard splits when I played two different synthesizers from the same keyboard? You can do the same thing with this multi-timbral keyboard synthesizer by assigning each voice its own channel number. Wind instrument players have fewer choices than keyboard players, but the choices are just as important. Most wind controllers are blown and fingered like a saxophone, while some have valves like trumpets. In either case, the keys or valves should feel responsive and comfortable. Some wind controllers let you take advantage of your saxophone or clarinet training, using the same techniques to control the reed in its mouthpiece and add expressiveness to your playing. Wind controllers that you just stick in your mouth and blow are easier to play, but they aren't as expressive. Wind controllers that feature only velocity sensing use breath pressure at the start of a note to establish a velocity value that determines the loudness of the entire note. Breath control is a more sophisticated option that lets you change the loudness of a note by blowing harder as you sustain it. Useful wind controller options include control over transposition, the capability to send program change messages, and choosing which of the 16 Midi channels you want to transmit over. Some wind controllers can automatically add a second melody line in parallel with the one you play, or sustain one note while you play others. Although many synthesizers can make drum sounds, a drum machine is often a better alternative. A drum machine is a synthesizer designed especially to produce drum sounds, with special hardware for programming and playing drum sounds. Instead of piano-style keys, drum machines have fingertip-sized buttons, one for each drum sound that's currently available. Each button generates a note-on message that triggers a specific drum sound. Many drum machines have at least 8 different drum sounds available at once, while some have as many as 16. The more sounds that are available at once, the better I like it. And as with any synthesizer, the best way to judge the quality of a drum machine's sounds is to listen to them. Like other digital musical instruments, a drum machine usually has a display window that describes what's happening inside the machine and prompts you for information. The display window should be large enough to read easily, and the messages should be clear and easy to understand. Make sure that when you buy any digital musical instrument, you'll be able to use it comfortably. Small is cute, but you don't want to get a headache from staring at it or have to file down your fingertips to fit. Better quality drum machines have velocity sensing buttons. Like velocity sensing keys, these usually produce louder sounds when you strike them harder. Some drum machines' buttons produce a smaller number of different velocity values than velocity sensing keyboards do. Even then, most drum machines respond to the full range of velocity data if you use a keyboard, sequencer, or other controller rather than the buttons to play the drum machine. Most drum machines have built-in sequencers that store and replay rhythmic patterns. Even though I use another sequencer, the one inside my drum machine is helpful. It stores short patterns that I can loop and combine to produce a complete drum track. The more complex the drum tracks you plan to create, the more patterns your drum machine must permit. Each individual pattern has a maximum number of notes or beats, so make sure before you buy a drum machine that its sequencer has enough notes per pattern and enough patterns per song for the kind of music you make. We'll examine sequencer features later on, and we'll see that they also apply to drum machine sequencers. Like other synthesizers, drum machines vary in their number of audio outputs. Some offer only a single output, others provide stereo outputs, while some have individual outputs for each drum sound, so that each can have its own signal processing. A good quality drum machine should be able to use more than just a single set of drum sounds, either by selecting a different bank of sounds from its internal programs, or by loading in alternate sounds from an external source. Some drum machines even accept floppy disks or data cartridges that contain the actual drum sounds of famous drummers. Almost anyone can play a drum machine, but skilled drummers usually prefer using Midi drum controllers. A drum controller is not a synthesizer like a drum machine, but a modified drum pad or kit that generates MIDI note-on messages when struck with drumsticks. Each message triggers a drum machine or other synthesizer. Drum controllers vary in size, from small pads to full-size drum kits that look much like conventional drum setups. Drum controllers should have as much expressive capacity and flexibility as other controllers. So look for such features as velocity sensing, provision for foot pedals and pitch bend controllers, and the ability to send MIDI program change messages. I also like to be able to assign each pad its own MIDI channel number, so that each pad can control its own synthesizer or its own patch. Sometimes I even use patches that make sounds we don't expect from a drum. After all, drum Phone controllers produce note-on messages just like a keyboard or wind controller. One great advantage of digital musical instruments is that not only can you play them, you can record and edit what you play. A sequencer stores a continuous stream of Midi messages along with the precise timing and order or sequence of each message. It acts like a smart tape recorder, not for sounds, but for Midi message data. Sequencers can be separate devices, or they can be built into a keyboard synthesizer, or be a program running on a personal computer. No matter how they're implemented, sequencers all work pretty much the same way. Here's how I build a sequence from scratch. I'll start by recording a bass drum part. Now I'll layer a tom-tom part on top of it. Now I'll add the bass. Next, I'll add an electronic fill. And finally, a lead part. I can keep adding parts, editing each one by copying, looping, and deleting sections, just like sentences in a word processor, until I have a finished piece of music. Sequencers use tracks to store data, much like audio tape recorders use separate tracks to store each voice and instrument. Extra tracks provide more flexibility and control. A sequencer may use a few dozen, or a few hundred tracks, but don't confuse tracks with Midi channels. Tracks are for storage, channels are for transmission. My rule of thumb is the more tracks, the better. I look for a minimum of 16 tracks so that I can store the data for each Midi channel separately. Some sequencers can move the start, end, or both start and end of each note to the nearest exact rhythmic unit of a value you specify. Depending on the sequencer, you may choose quantizing while recording or later during editing. In either case, quantizing the note on and note off of a string of eighth notes to the nearest eighth note value assures that each note will begin and end precisely on the beat. When passages are difficult to play up-tempo, but easier to play at a slower speed, you can slow the sequencer's metronome during recording then reset the metronome to a faster tempo during playback. Unlike audio tape recorders, speeding up the playback did not change the pitch. If a part is too difficult for you to play at any tempo, or if, like me, you're not much of a keyboard player, you can step record the keyboard parts. For example, I'll assign a 16th note to both duration and step advance values. Then, with the sequencer set in step recording mode, each time I play a note, it is automatically assigned a duration of a 16th note, no matter how long or how short a time I hold down the key. The next note I play is assigned to the next 16th note, no matter how much time has elapsed between notes. Here's what it sounds like. Your sequencer should also let you edit the program change messages that cause the synthesizer to change its instrumental sound or patch. Then, if I don't like a passage played with a piano sound, I can insert a program change message and select another sound, like a flute. Furthermore, Midi does not specify that any particular program number be assigned to any particular sound. So if I record a sequence on this synthesizer using patch 21, acoustic piano, and play it back on this synthesizer, patch 21 might be a completely different sound. I don't like those kinds of surprises, so I make sure I can add, delete, and change program change messages within my recorded sequences. Although all MIDI sequencers record the same kinds of information, not all of them could exchange files until the advent of standard MIDI files. Now you can record a sequence and store it on a diskette to share with other members of your band to use in their sequencers. Most sequencer programs give you the option of storing your data as a standard MIDI file or SMF, often called exporting, or loading a sequence stored in SMF format from a diskette, called importing, so that you can take advantage of SMF compatibility among different sequencers. You can even buy diskettes of popular songs arranged as standard MIDI files. You can change an arrangement or slow it down and mute one instrument so you can learn its part. Standard MIDI files let you work on the song without having to enter all the notes. But there's a problem in the MIDI specification that even standard MIDI files won't solve. A unique program number identifies each synthesizer voice or patch. Each voice or patch represents a single instrument sound or sound effect. The MIDI specification does not establish a correspondence between particular program numbers and specific patches. So, for example, the same program change message might select a flute patch from one synthesizer and an electric guitar patch from another. General MIDI, an addendum to the MIDI specification, addressed the problem of patch number incompatibility among different synthesizers. It established a standard list of patches and their corresponding program change numbers. General MIDI is optional, so synthesizer manufacturers are free to implement or ignore it as they wish. The most important aspect of General MIDI is its instrument patch map, a list of 128 sounds and corresponding MIDI program numbers. The sounds are loosely grouped into 16 families, each with 8 variations. The families include such familiar sounds as pianos, guitars, brass, reed, and percussion instruments, as well as widely recognized synthesizer sounds, sound effects, and ethnic instruments. Sounds other than the 128 specified by General MIDI are assigned program numbers unique to each synthesizer. This keyboard controller is designed for General MIDI. It even has the name of each instrument in the General MIDI patch map alongside the program change buttons that send each patch number to a General MIDI tone module. If you connect this keyboard to any General MIDI tone module and use the button that selects an ensemble string sound, you can be sure you'll get an ensemble string sound from the tone module. General MIDI also includes a percussion key map that assigns each drum sound to a specific MIDI note number. Although the MIDI specification itself does not require that any particular sound be assigned a specific MIDI channel, General MIDI restricts drum sounds to MIDI channel 10. A synthesizer that complies with the General MIDI standard must respond to all 16 MIDI channels, with a minimum of 24 voice polyphony and dynamic voice allocation. Other requirements of a general MIDI synthesizer include velocity response and implementation of pitch bend, aftertouch, sustain, and volume controllers. Since General MIDI specifies a predictable set of sounds, you can even buy royalty-free standard MIDI files intended for General MIDI synthesizers and use them in multimedia presentations the same way you use clip art. Then, for example, you can use your sequencer to play a song faster or slower to fit the length of a video scene, or add program change messages to choose different instruments. If you are buying two MIDI devices that work together as a system, such as a controller and synthesizer, both must implement a particular feature if you want to be able to use that feature. For example, this wind controller transmits breath pressure data, but this synthesizer does not respond to breath pressure, so it doesn't apply. Fortunately, there is an easy way to predict compatibility: MIDI implementation charts. Most manufacturers include them with their MIDI equipment. The charts are one of the best ways to compare the features of MIDI devices. I have a notebook where I keep the chart for each device in my MIDI network. The leftmost column of each chart, labeled Function, lists categories of MIDI messages. The second column, Transmitted, indicates whether the device can generate that particular type of MIDI data. The third column, Recognized, indicates whether the device will respond to that particular type of MIDI data. Any MIDI device can receive any type of MIDI message, but a particular device can respond only to certain categories of messages. Finally, a fourth column lists remarks. For each message type, there will be an O in the transmitted column if the device transmits that message type, or an X if the device does not transmit that message type. An O or X in the recognized column similarly indicates whether the device can or cannot act upon that message type. This controller's implementation chart shows an O in the transmitted column for pitch bend, and this synthesizer's implementation chart shows an O in the recognized column for pitch bend. So when I do this, it works. If either chart had an X for pitch bend, it wouldn't have worked. A MIDI port either transmits or receives data, never both. Signals on a particular MIDI cable travel in one direction only. A cable connected to a MIDI out port carries data away from that port to the MIDI in port of a second device. When one device controls another, like a keyboard controller and a tone module, the keyboard controller becomes the master and the tone module is called the slave. A single cable connects the MIDI out port on the master keyboard controller to the MIDI in port of the slave tone module. If two devices must exchange signals, like a keyboard synthesizer and sequencer, a second cable is necessary. During recording, one cable transmits data from the keyboard's MIDI out to the sequencer's MIDI in. During playback, a second cable transmits data from the sequencer's MIDI out to the synthesizer's MIDI in. If you have more than two MIDI devices, you can connect them in a daisy chain using MIDI through ports. I'll start by connecting the MIDI out jack of the master keyboard to the MIDI in jack of this synthesizer. Now I'll connect a cable from the MIDI through jack of this synthesizer to the MIDI in jack of the next synthesizer. I can repeat the MIDI through to MIDI in connection for each successive device in the chain. If one of your instruments lacks a MIDI through port, just put it at the end of the daisy chain. Now my master keyboard controls all these devices. The MIDI specification designates 4 different modes, although one of them is no longer widely used. Each mode describes how a MIDI device should respond to messages that include a channel number. If a slave device is set to mode 1, often called Omni mode, it will respond to any data transmitted by the master, regardless of the channel number. Mode 1 is most useful for testing or troubleshooting a MIDI setup because channel numbers don't matter. If 2 devices are cabled together properly and the slave is set to Omni, the slave should respond to notes transmitted by the master over any MIDI channel. Mode 2 has little use, so most MIDI devices no longer even implement it, and we won't even worry about it. In Mode 3, the slave responds only to messages transmitted over a single specified channel. The most important consideration in using Mode 3 is that the master and slave must communicate over the same channel if the slave is to respond. If I set my master keyboard to transmit on channel 7, and my slave synthesizer to respond to channel 5, I won't hear anything when I play the keyboard if the synthesizer is set to mode 3. But if I set the slave synthesizer to channel 7, the same as the master keyboard, I can hear sounds as I play. In mode 4, often called multi-mode, a slave synthesizer can route each incoming message to its specified channel and assign each channel a different sound. The number of different instrument voices that can sound at once is limited only by MIDI's 16 channels and the synthesizer's multi-timbral capacity. Mode 4 is the most powerful because I can play a sequence using only a single multi-timbral synthesizer. Messages tagged with channel numbers will find their way to the proper voice. If a problem occurs, like no sound, and you cannot determine which device is causing the problem, begin with the cables. MIDI cables cause more problems than any other part of the system. Start with the device where the MIDI data originates, usually a keyboard controller or sequencer. Follow the cable from the MIDI out jack of that first device and make sure it's connected to the MIDI in jack of the device that's supposed to receive the data. Follow each cable in a similar fashion until you are sure that all the cables are connected properly. Drawing a signal flow diagram showing each device and data path is helpful. That step alone solves a great many MIDI problems. Much of the troubleshooting process is based on isolating the problem before trying to solve it. If a particular device is not responding at all, check to see that the power is turned on. Then try using different MIDI cables. Check the volume and slowly increase the setting of any volume control that is off, muted, or at a very low setting. If the physical connections, power switches, and volume controls are not the cause of the problem, channel assignments may be. Set the slave device to mode 1 or Omni. If it responds at all, you can be sure that MIDI data is getting through over at least one channel. The master may be transmitting on a channel the slave is not set to receive on. Setting the channel assignment on the slave to the same one as the master should solve the problem. Sometimes the wrong device responds, or devices may respond strangely, making it difficult to isolate the problem within the context of a complex MIDI system. In that case, power down, unhook everything, and choose a single transmitting device and a single receiving one. Use a single MIDI cable to connect the transmitter's MIDI out jack to the receiver's MIDI in. If there is no response after powering on, try repeating the process with a different transmitting device, a different receiver, or different cables until a MIDI system of 2 devices works properly. Reconnect one device at a time and continue the process until everything is working as it should, or you have identified and fixed or removed anything that isn't working properly. Digital musical instruments open up an exciting new world to composers, performers, business people, and music lovers of all kinds. We hope that this tape has shown you some of the ways you can use digital musical instruments and MIDI, and that it will help you get started. It's a great time to be a musician. Digital musical instruments make it possible for almost anyone to enjoy the satisfaction that comes from music making. The best way to find out what's possible is to try. So let's get to it.
There's a lot more to know about digital musical instruments than one tape can possibly hold. For an in-depth discussion of every aspect of digital musical instruments, we recommend that you read Midi, A Comprehensive Introduction by Joseph Rothstein, the executive producer and host of this videotape. Dr. Rothstein has taught thousands of people to use digital musical instruments effectively, and his book is used in classrooms and by musicians across the country. To order the book or more copies of this videotape, call toll-free 800-736-0700.